2.3 Applying Newton's Laws. We'll start with objects in equilibrium. An equilibrium state is a state in which an object has no forces acting on it. We say that the net force acting on the object is 0. Let's start right away with sample problem number 1. A sled has a mass of 14 kilograms and is on a hill that is inclined at 25 degrees to the horizontal. The hill is very icy, so friction is negligible, and the sled is held at rest by a rope attached to a post. The rope is parallel to the hill as shown. Part A. Calculate the magnitude of the tension in the rope. Let's start by drawing a free body diagram of this object on the incline of 25 degrees. We'll use a dot to represent the sled. We will say that the direction up the incline is positive and perpendicular to the incline is positive. We'll call this the x direction. This is the y direction. There's a force of gravity acting on the sled in the downward direction, and it's equivalent to the mass times the gravitational field intensity. Since the object is being held by a rope, there's a force of tension acting up the incline parallel to the incline. The force of gravity can be broken up into x and y components. Now, if we examine using trigonometry, and we see this angle is 25 degrees, then this angle is 90 minus 25 degrees. If this angle is 90 minus 25 degrees, then this angle must also be 90 minus 25 degrees by the transverse parallel line theorem, Z pattern. That means that this angle inside the interior angle must be 25 degrees. Now, since the object is resting on the incline, there will be a normal force that's perpendicular to the incline. And the normal force will be equivalent to the y component of the force of gravity, which is the adjacent, so mg cos 25 degrees. Whenever we have an object on an incline, the normal force will always be equivalent to mg cos theta. Now, the force that is causing this object to accelerate down the incline is the x component of gravity that is in the same direction as the incline. Whenever an object is resting on an incline, the acceleration down the incline will be equal to, since this is the opposite with respect to the hypotenuse and angle, mg sine 25 degrees. So the acceleration due to gravity down an incline is always equal to mg sine theta. This will be true anytime an object is on an incline. So remember these 2 points. So let's calculate the magnitude of the tension in the rope. We know that the sum of the forces in the x direction is 0 because it's in an equilibrium state. And we will use a two-star method that we've used in previous examples. And we'll start by listing all the forces acting in the x direction. So we have plus the force of tension, it's acting up the incline, and minus the force of gravity in the x direction. We can replace this with the x component of the force of gravity, which is mg sine 25 degrees. So we can see if we rearrange this, that the force of tension is equal to mg sine 25 degrees, which is 14 kilograms times 9.8 newtons per kilogram times the sine of 25, and we get 58 newtons. So in this example, the magnitude of the tension in the rope is 58 newtons. In part B, we want to calculate the magnitude of the normal force acting on the sled. We know that the sum of the forces in the y direction is also 0. In the y direction, we have two forces. We have the normal force acting up and the y component of the force of gravity acting down. We'll use a two-star method, listing all the forces acting on the object using plus or minus to indicate direction. We have plus normal force minus force of gravity in the y direction. For the force of gravity in the y direction, we will write mg cos 25 degrees. If we rearrange this equation, we end up with a normal force is equal to mg cos 25 degrees. We bring this over, remember it becomes positive, and we can calculate the normal force as 14 kilograms times 9.8 newtons per kilogram times the cos of 25 degrees. Punch this in, and we end up with a normal force of 120 newtons, or 1.2 times 10 to the power of 2 newtons. Next, we'll take a look at sample problem number 2. The traction system stabilizes a broken tibia. Determine the force of the tibia on the pulley. Neglect friction. So we have a free body diagram. We have a pulley that'll be attached to a mass of 18 newtons down. So the force of tension will be 18 newtons. Since we have 18 newtons pushing down and it's attached to this one string, will have a tension of 18 newtons. So in this diagram, we have 18 newtons we'll call this force of tension 1. This is happening at an angle of 57 degrees. And then we have a force of tension pulling in this direction. We'll call this tension 2. It's also 18 newtons. And it's acting at an angle of 32 degrees. We can break these forces into X and Y components. Force of tension 1, X. Force of tension 1, Y. Then we have force of tension 2x and force of tension 2y. Now the y component is the opposite with respect to the force of tension. So it's 18 sine 57 for tension 1 and 18 sine 32 degrees for tension 2. The x component is the adjacent, which is 18 cos 57 for the first tension and 18 cos 32 for the second. So let's establish that up and right are positive. And in this situation, the tibia will be exerting a force in this direction. We'll call this the force that the tibia is counterbalancing. It can be broken up into force tibia X and force tibia Y. So let's find the sum of the forces in the x direction. Since it's in equilibrium, the sum of the forces is 0, and we're going to add up all of the forces in the x and y direction using plus or minus to indicate direction. We have 3 forces. So using our 2-star method, as we used before, zero equals plus tension 1x plus tension 2x minus force of tibia x. So we can substitute. This is plus 18 cos 57 degrees plus 18 cos 32 degrees minus force of tib x. We can rearrange for the force of tibia x, and we get 18 cos 57 plus 18 cos 32. Punch this into our calculator, and we end up with 25 newtons. So the magnitude of the force of tibia in the x direction is 25 newtons. Let's do the same for the sum of the forces in the y direction. We know it's in equilibrium, so the net force in the y direction is also 0. Let's list all the forces in the y direction using plus or minus to indicate direction. We have 0 equals. Now we have force of tibia, force of tension 1, y component up, force of tension 2, y down, and the force of tibia, y down. So using plus or minus to indicate direction, we get plus force of tension 1y minus force of tension 2y minus force tib y. So 0 equals plus 18 sine 57 minus 18 sine 32 minus force of tib y. If we rearrange, the force of tibia in the y direction is plus 18 sine 57 minus 18 sine 32. If we calculate this, we end up with 5.6 newtons. So we can calculate the total force that the tibia is counterbalancing the pulley system by finding the square root of 25 squared and 55.6 squared using Pythagorean theorem. If we solve this, we end up with 26 newtons. To find the angle at which this is acting, this force is acting, we'll use the inverse tan of opposite over adjacent, opposite being 5.6 and adjacent being 25 newtons. Theta ends up being 13 degrees. So the force of the tibia on the pulley system is 26 newtons, 13 degrees below the horizontal. Next, we'll look at accelerating objects. If an object is not in equilibrium, then the object will accelerate in the direction of the net force. So the sum of the forces is equal to mass times acceleration. Let's start by looking at sample problem number 1. A sled is at the top of a hill, which makes an angle of 18 degrees with the horizontal as shown. The height of the hill is 25 meters. Calculate the speed of the sled as it reaches the bottom of the hill, assuming that no friction acts on the sled. All right, first I want to examine if the height of the hill is 25 meters and we have an individual on a sled. This individual will slide down this distance, and we want to find the speed as it reaches the bottom. The distance it will travel, this distance here, We can calculate by using the angle, 18 degrees, the opposite of that angle, 25 degrees, and the hypotenuse, delta D. Opposite hypotenuse is the trigonometric ratio sine. So we can write sine theta equals opposite over hypotenuse. So delta D is equal to 25 meters over the sine of 18 degrees. Punch this into our calculator, and we end up with actually, I'm going to leave this. I'm not going to calculate it. I'll leave delta D as this right here. 25 over sine 18 degrees. Okay? So eventually we want to find the final speed. We know V1 is 0. We can calculate delta D. What we'll need to find now is the acceleration. In order to find the acceleration, we're going to draw a free body diagram of the sled. It's acting on an incline of 18 degrees. It's a force of gravity acting down. This force of gravity can be broken up into x and y components. By the transverse parallel line theorem, and using our knowledge of trig, we know that this angle is 18 degrees. So the x component of gravity is mg cos theta, or 18 degrees, and this would be mg sine theta, where theta is 18 degrees. If we examine the sum of the forces in the x direction, we'll make x be the direction of the incline and y perpendicular. And we know that the object is accelerating. We can list all the forces acting in the x direction. So we have one force. We'll use plus or minus to indicate direction. So mass times acceleration is equal to plus mg just realized I made a mistake here. This is the opposite, so this is sine. And this is the adjacent, so this is cos. And we should know that from above, that the acceleration due to gravity down an incline is always mg sine theta. Apologize for that mistake. In this expression, we have m on both sides of the equation, so we can cancel it out. So we know the acceleration is equal to g sine theta. We're going to put this value in for A. So V2 is equal to the square root of 0 squared plus 2 times g sine theta, and delta D is 25 over sine theta, where theta is 18 degrees. If we have sine theta on top and on the bottom, we have V2 is equal to 2G 25. That's the square root of 2 times 9.8 times 25 meters. If we punch this into our calculator, we end up with a final speed of 22 meters per second down the hill. All right, for the next example, we have a crate with a mass of 32 kilograms on a frictionless surface and connected to a second crate by a string that passes over a pulley. The second crate has a mass of 40 kilograms. The pulley is frictionless and has no mass, and therefore will have no effect on the motion of this object or system. The string also has no mass. Determine the acceleration of the system of crates and the magnitude of the tension of the string. So let's look at this one. This crate is attached to a string to the second crate. Gravity will pull down on mass 2, causing this whole system to move to the right and down. For that reason, we are going to let right and down be positive. And we'll draw a free body diagram of crate number 1. This is M1. And crate number 2. Might as well redraw it. If we examine crate 2, we know that a force of gravity is acting down on it, which is equal to m2g. And since it's not free falling, it's connected by the rope, there will be a force of tension acting in the upward direction. Mass number 1 is being pulled to the right by a force of tension. And I've written the force of tension in both free body diagrams in red, because since they are attached by the same rope, they will have the same tension. So let's examine the forces acting on mass 1, and then the forces acting on mass 2. We will use plus or minus to indicate direction. For mass number 1, we know the sum of the forces is equal to positive force of tension. So mass 1 times acceleration equals plus force of tension. Let's look at the sum of the forces on mass 2. Using plus or minus to indicate direction, we get plus force of gravity minus force of tension. We'll replace the term net force with m2a. We'll replace the force of gravity with m2g. And we'll draw our tension in red. Now we need to solve for the acceleration of this system. But we also have a second unknown, which is the force of tension. So we're going to use substitution or elimination to allow us to solve for the acceleration. Let's rearrange this first free body diagram for the force of tension. In this case, the force of tension is equal to M1A. In the second example, let's rearrange this for the force of tension. I'm going to bring the force of tension over the equal sign. It'll become positive. I'll bring M2A on the other side. It'll become negative. And we are left with plus M2G minus M2A. Now, since tension equals M1A and tension also equals M2G minus M2A, then we can say that M1A is equal to M2G minus M2A. In the determination of acceleration, we're going to bring all the like terms together. We'll collect like terms. We have M1A plus M2A equals M2G. We'll factor out an A. We have M1 plus M2. Divide both sides by M1 plus M2. We end up with acceleration equals M2G divided by M1 plus M2. Now this looks, folks, familiar. It is as if we are saying acceleration is equal to net force divided by mass, where the net force that is driving this acceleration is the force of gravity of the hanging mass. That is the whole reason why this system is accelerating, divided by the mass. In this case, it's the mass of the system, M1 plus M2. If we sub and solve, we end up with 40 kilograms times 9.8 newtons per kilogram divided by 32.5 kilograms plus 40 kilograms. Punch this in, and we end up with an acceleration of 5.4 meters per second squared. Now, what if we had to calculate the tension in the rope? Well, we have two equations we can use to find tension. You can use either this one or that one. You will get the same answer because there's one rope, therefore one tension. I'm going to use this one. It's much simpler. So the force of tension equals M1A. Mass 1 is 32.5 kilograms times an acceleration of 5.4 meters per second squared, or 5.4 newtons per kilogram. Punch this in, and we end up with a tension of 120 newtons. Oh, my apologies, that's 180 newtons. Rewrite that. Okay, be sure to try the homework problems. Good luck.